E. coli cell. E. coli. And it has on its surface a number of receptors. And it will produce and secrete a molecule that is typically referred to as an autoinducer. Autoinducer. Inducer. And that's what this little spear represents. Other bacteria are also producing autoinducers, but they're producing different ones. Here I've got some streptococcus, and this producing little squares. In general, gram-negative bacteria produce autoinducers that are referred to as homoacyl lactose. There's a whole bunch of lactose. Homoacyl lactose. And gram-positive, in general, nothing's cast in stone here. There's no real absolute difference here. But the gram-positive, in general, produce short-chain oligopeptides as autoinducers. Now, when the population density is low, as it would be down in here, bacteria cells are producing these autoinducers, but they're not combining with receptors that would be sufficient in density to initiate any type of behavior modification. Here we've got a little sphere, and here we've got a little cut, there's a little cut, there's a square, there's a W, there's a different type of receptor. There's receptors for many different types of bacteria. So in a mixed population, we've got some sunless up here, and it might be producing a star. These are stars that's producing autoinducers. And somewhere on this particular cell here, we've got a receptor. A star. So as the population density increases, as more and more autoinducers have been produced, more and more of them begin to fill the receptors on the surface of the cell. And that sends a signal into the nucleoid saying, hey, we're getting crowded here. And it begins to modify its growth. It has receptors for itself, and it has receptors for a variety of other different types of bacteria. This typically happens when the cells enter into mid to late exponential phase growth. Showing it right here. There's an inflection point there theoretically at this point, and you can't see it here on the graph, but because you can detect it in the cells themselves. It's starting to produce materials that are going to enhance its ability to survive in a competitive world. These now turn to what are called secondary metabolites. Secondary. It's no longer balanced. As it begins to shut down, some of that ATP that it was producing is stockpiled. Some of the carbohydrate that it may have been producing, some of those sugars will be produced in a starch granules or lipid granules, or in the case of a fat, PHP. Secondary metabolites. These are involved with survival in a competitive environment. Now again, remember, this is a pure culture. This is a xenic culture. It's got only E. coli or whatever it is. But in nature, out there in the soil, out there in your intestinal tract, these organisms are producing these autoinducers, and they're influencing other bacteria as well as itself. Secondary metabolites. What are some examples of secondary metabolites? Have you ever heard of heat shock proteins? HSPs. HSPs are proteins that are produced, they were discovered just as an enzyme in response to elevations of temperature. got a bacterial cell that's capable of producing an endospore. This is when it will undergo that process. The 7 stages that we talked about, you don't have to remember those, but remember, it began to divide asymmetrically. We had 4 in the mother cell, we had development. All of this begins to happen during the exponential phase, during secondary metabolite. And from your standpoint, one of the most important types, what else do you suppose might be very important as a secondary metabolite? Something that would inhibit the growth of other organisms in a competitive environment. How about antibiotics? Antibiotics. We talked about many different bacteria producing antibiotics. They don't produce it during every phase of the growth curve. Typically, will only produce it during late exponential growth. Late exponential growth. Okay. Does that make sense? Okay, let's talk about something else. We say that this curve, this exponential growth curve, is representative of an asynchronized culture. An asynchronous culture. A means without synchrony. So what would a synchronized culture look like? Yeah. Continue to grow to beyond. No. But how does that curve differ between an asynchronous culture, or asynchronous growth, and a synchronized culture, or synchronized growth? Think of what that means. An asynchronous culture simply means that at any one point in time, let's just picture this point right here. Some of the cells are in that, we talked about the B phase. Some of them are pre-B, some are mid-B, some are late-B. Some of the cells are in pre-C, some are in millosynthesis, some of them are coming out of synthesis. Some are dividing, some are preparing to divide, some are dividing, and some are just coming out of the division. So that's 9 different phases right there that we can pigeonhole these cells into. Go ahead. Exactly right. It would look like a stair step. Because if it's synchronized, all of the cells are doing everything, doing a particular part of the cell cycle at the same time. They're all synthesizing new chromosomes. They're all preparing to divide, and they all divide at the same time. So rather than looking like that, three cycles is about all you can keep it in synchrony. But this is what it would look like. All of the cells are at the same point. So they come up to here, they begin to grow, they begin to lengthen, they make more chromosomes, and then during the D phase, they divide. All of them at once. One big jump up. They all come out of that at the same point. Another round. You say, well, okay, I understand why that is. Why is that important? Why is that important? Well, let's think about this. Does a particular cell produce all the enzymes that we might be interested in throughout its cell cycle? Probably not. Probably not. Think about the endospore producing. All those genes and all those enzymes and proteins are involved in the formation of an endospore. They're not going to be produced during growth in which the cells do very well. We want to be able to manipulate that population so that we get as many cells at that particular point where we're getting ready to produce an endospore as is possible. That way we've got, rather than, let me say, 9 different phases, rather than 10% being in any one particular phase, now we've got 90, 95, maybe even 98% at that point where they're ready to produce that endospore. That's where we're going to find a large percentage of the cells that have that enzyme, so all we have to do is harvest those cells and purify that enzyme and study. Whereas, up to that point, we would have to look at want to do that, maybe there's a protein just before the cell, how about this? There's a protein called XYZ that's involved in septation, breaking the cell into the $2 cell. Yet we're not going to find it in cells that are in B growth. We're not going to find it in those cells that are in C growth. It's only going to be those that are in late D growth. So we need to get as much of the population in late D growth as possible, so that we've got a population cell we can work with, so we can purify that material. XYZ. Does that make sense? Maybe. Well, it is important that we do so, because this is how we get the workable quantities of these enzymes and proteins. The next question is, how would we synchronize the culture? How would we synchronize it? Any ideas? Let's take an example of something you would be familiar with. In the class, we use the example of Kentucky Derby. Horse race. First of May, I think, somebody said, the first of Saturday. Everybody heard of Kentucky Derby? Everybody seen the Kentucky Derby? Maybe not, but in any horse race, you suppose they just shoe all the horses onto the field and then run around, and whoever comes around first is the winner? Something like that? Never saw a horse race at all, did you? You have a starter gate, yes. You have a starter gate. In other words, they bring all the horses, all the jockeys onto the field, and they put them into a starter gate. They're all brought into that gate, and they're left right there. At that point in time, they're all at the same point on the track. So how could we get cells physiologically at the same point of their metabolic metabolism? Don't take away all of them. Take away one. Take away a vitamin. Take a vitamin. All the cells then will metabolize until they get up to the point where they need that vitamin. Without it, they stop. They stop metabolism. They stop growth. And you, depending upon the culture, depending on how fast they are capable of growing, typically like 3 or 4 hours, you say, okay, all the cells should be at the point where they need vitamin XYZ. Now I'm going to put vitamin XYZ into it, and they're off to the races. Now the cells take XYZ, they utilize it, they go to the next step. The next step, to the next step, and then they're dividing at the same rate. They're, at that point, they're all at the same part of the cell cycle simultaneously. They're simultaneously at the same point of the cell cycle. Now, even in a clone of cells, some of them are going to start to do things faster, and it breaks down after about 3 of those cell divisions. But that's how we study enzymes and proteins that are found in very low concentrations and only at a particular point of the cell cycle. By lining them all up so that we can get them to the same point, and then